Welcome back to the class of differential equations, and we are working on section 4.2 and 4.3. This is the linear second-order homogeneous differential equation. Furthermore, indeed, those coefficients are constants. Okay, and what we just said in the previous video, well, such a differential equation always we can create a matching polynomial and a characteristic polynomial equation. For the second order, we are having a quadratic characteristic equation. And then such a differential equation always can be solved using the following arrangement. They are just based on the solutions of the characteristic quadratic equation. So there are three cases. The first case, when we are having two real number roots. So the solution will be in the form of the linear combination of those two exponential functions. And also in the case when we are only having one single root, a single root with multiplicity 2, and then we are having the linear combination of the exponential function and the t times the exponential function. The third case is we are having two complex roots, and then if that is the case, you need to identify the real root and the real part and the imaginary part, the real part and the imaginary part. And then the solution, it is arranged as the exponential function e to the power of the real part times t times the linear combination of cosine and sine. The function cosine and sine, it is in the form of the imaginary part times t. But let's work on this first example first. Okay, we are having a second order linear differential equation, and it is homogeneous with constant coefficients. So accordingly, we are having a characteristic polynomial, and indeed there are two roots as we already solved it in example 1. So specifically this time the solutions are like this. The solutions are like this. The linear combination of two exponential functions, linear combination of two exponential functions. C1, C2 are the arbitrary constants. C1 times e to the 3t and e to the C2 times e to the 1/2 t. And also I hope you remember those two exponential functions, indeed not only they are different, they are linearly independent. Linearly independent. Okay, so this is the first case. And also, just for reminding purpose, well, the reason we are having those two linear combination of two linearly independent functions, because in general, the solution of the second order linear differential equation is the vector space of dimension 2. So I hope you see we are having the basis. Okay, the solution, it is the linear combination of the basis that does represent all the solutions. All right, let's look at another case. What will happen if I'm having the differential equation in this fashion: y double prime minus y equals 0. And I hope you can tell this time the characteristic polynomial equation is r squared minus 1 equals 0. And no doubt there are two real roots, 1 and a negative 1. So accordingly, the solution can be written as the linear combination of two exponential functions, as we just explained. Why we got a linear combination of those two exponential functions. Okay, R1 equals 1, that's e to the t. R2 equals -1, that is e to the -t. Okay. And also I do have another similar example. What would happen if I change this minus to plus? Algebraically, usually it may not change the things dramatically, but anyway, you want to see in the case of differential equation, the situation is totally different. Because starting from the differential equation like this, we are having the characteristic equation in this fashion, right? And indeed, we cannot say 1 or -1 is the solution, not at all. And indeed, for the characteristic equation here, we are having two complex roots, I and the -I. I, it is the imaginary unit, which is really square root of -1. So in this case, I'm looking at the second arrangement of the general solution. We are having actually third arrangement, two complex roots, okay? Two complex roots. So clearly, the real part for example 6, part B, the real part is 0, alpha is 0. And the imaginary part, it is, well, if you insist, you can say the imaginary part is 1 or -1. But indeed, when we solve differential equations, we always take a beta as +1. Take a beta, the imaginary part as positive. So accordingly, what we are having here is, well, the third arrangement for two complex solutions. E to the alpha t, then the linear combination of cosine and sine. Alpha is 0, so surprisingly, the actual solution does not have the exponential term at all. But we do have cosine and sine. As I said, you do take the real imaginary part as positive. So it tends to be cosine t, sine t. So indeed, in the end, the solution is C1 times cosine t plus C2 times sine t. Okay, two similar problems. But anyway, the solution of those two look-like problems are totally different, right? The linear combination of two exponential functions, and then linear combination of two trigonometric functions. Let's work on another case. Example 7. Okay, solve a differential equation like such. And we know we always create the characteristic polynomial equation first. So in this case, it is r squared minus 2r plus 1. And indeed, we know this is a perfect square. So indeed, there's only one root. Or if you want, we can say there is one root with multiplicity 2. And then according to the arrangement in the table, in the arrangement as I typed on the previous page, there are 3 cases, right? This is the case in the middle, when we are having one single root with multiplicity 2. And then the solution, it is a linear combination of exponential function, then with an extra t times the same exponential function. So accordingly, the solution for example 7, this is C1 times e to the t plus C2 times t times e to the t. Okay, or it is 1 here, or it is 1, or it is 1, or it is 1, or it is 1. Okay, so this is the solution we are having. And example 7. And I'm going to save example 8 for a little bit. Thank you for watching.